This video demonstrates that Stonehenge is a neolithic sundial and uses a 30-hour time system. The traditional numbering of pillars is based on the summer solstice alignment, but if we're thinking of the arrangement in terms of time, that numbering system doesn't really make sense, and it makes more sense to think of things in terms of the cardinal directions, true north and south. These are what we think of when we align a sundial. And north is in this position here, which would actually be a gap. This is a lintel. Now, if we take the 24-hour day and divide it by 4, obviously we get 6 in the morning and 6 in the evening, represented by 6. Another way of thinking of that is 6 and 18. Well, if we divide 30 by 4, we get 7.5. We can think of those same positions as 7.5 and 22.5, or half 7 in the morning, according to a 30-hour time system. Obviously 6 a.m. and 6 p.m. Are the times that the sun rises and sets on the equinox, when it rises at 90 degrees and sets at 270 degrees. And these are obviously the right angle positions to north. So if north is in this position, and we're thinking of the right angle, if north is 360 degrees, then we count 0, 1, 2, 3, 4, 5, 6, 7.5. So this position would be precisely east. When the sun's behind this pillar at the centre of it, it will be on due east. And we can see it comes down. It would strike the centre of this pillar. However, trilithon 4 obstructs its path of direct light. And if you think light always travels in straight lines, and the lines would always run parallel, this light would also run and come through this gap and strike further along, essentially meaning the monument displaces the light and places it effectively ahead of time. But of course, the sun doesn't rise in the sky and travel 360 degrees around the sky, unless of course you're very far in the north hemisphere or south hemisphere and it's your summer. For most of us, the sun roughly appears to travel a 180 course over the sky, which is usually represented as a semicircle on a sundial, and that kind of gives the clue of how we read time at Stonehenge, with our positions condensed into half of the circle. So we count one position as one unit, one gap, then one pillar, then one gap, then one pillar. These would be the different hour positions. Obviously, when the sun's over here in the morning, the light would be shining over this way. I'm going to show you some video footage in a moment of that happening. I just want you to take a look at these this kind of formation here. This is the west side, and we're missing a number of pillars. This will be, as I've said, 7.5 reading time. So we can think of this pillar as 7. This will be 8. There should be another pillar here which is actually missing. It's one of the missing pillars of the monument, but this will be 9. Then there'll be a gap here which would be 10, and this is pillar 21, but it would be the 11th hour, 11. Got this gap here which would be 12, and then this pillar here would be 13. These are all positions that would be struck from a line coming from trilithon 4, and at this point pillar 13 is when the line would actually disappear. It would fade away due to the angle where the sun is by that time. It no longer can get through this gap, and it fades at this point. This footage was filmed on August the 25th, 2019. The first thing we need to try and understand about the Stonehenge monument is why trilithon 4 obstructs the light travelling along the east to west meridian. It has the effect of displacing it by this gap, and it has the effect of calibrating the monument to a date other than the equinoxes, and it's actually calibrated to the date that's precisely halfway between the spring equinox and the summer solstice. This date is May the 5th, the date where traditionally people would celebrate Beltane. So on May the 5th, when the sun is at the azimuth positions that relate to the on the hour points, when we divide the day into 30 hours, and still referencing local mean time. The monument, specifically the T4 line cast by Trilithon 4, points to positions on the outer circle that relate and correlate to those times. So this is the western section of the circle. I was showing you this before. We can see this is Trilithon 4. We're looking here at pillar 21. This is the T4 line. You can see the T4 line is currently in this gap area preceding pillar 21. If we just look further along, this large gap area here is where we've had the missing pillar. There was a pillar here at some point, but it has since been removed. This is pillar 19, which was the west position, facing opposite, obviously facing due east, and this is the point where on the equinox the sun will be rising directly opposite this point. So this is 7.5 in our 30-hour time system. So this pillar overall represents the 7th hour. This here is a lintel. It would have been raised up in the air when the pillars were here, and this would have been a gap, and this would have represented the 8th hour when the beam of light passed off this pillar onto this gap. It would have been considered as moving from the 7th hour to the 8th hour. Obviously, where we have our missing pillar, this would be the 9th hour, and so our beam of light, our T4 line, is on the 10th position in the 10th hour. And considering the pillar would have ended somewhere around here, we can think, or we can see, the line is roughly halfway along that position. Now, I'll just move this along a little bit. I have to apologise because it's a bit blurry here to watch, but we can see we've got roughly 9:22. This is August the 25th, so this is in British summertime. So we have to convert this back to GMT, Greenwich Mean Time, which gives us 8:22 in the morning. Now, we need to convert that time into 30-hour time. So we divide the number of minutes with 22 by the 60 minutes of the 60-minute hour, and this gives us the percentage of the hour those minutes represent. You have to use the quotient between the degrees per hour rate of the time system. So in the 24-hour time system, the sun moves 15 degrees per hour. In the 30-hour time system, it moves 12 degrees per hour. And if we divide 15 by 12, we arrive at 1.25. So that's our quotient. So it's 8:22 in the morning, and this figure represents 22 minutes as a percentage of the hour. We times this by the quotient, and we arrive at, obviously, the 10. This gives us the hour, 10th hour, which is our 10th position, and we have to figure this out in terms of minutes. This is the percentage of the hour. So of course, if there are 48 minutes in a 30-hour hour, that's because 1,440, the total minutes in a day, divided by the 30 hours of the day, gives us 48 minutes per hour. So the amount of seconds in the minute has to be a base 10 fraction of how many minutes there are in the hour. So we've got 48 seconds in a Stonehenge minute times 45.83 recurring. This poetic license, because we're using recurring numbers, this is basically 22 minutes past. So this is telling us that 22 minutes past 8, 24-hour time is 22 minutes past 10, 30-hour time. So of course, with this position here being position 10, we'd expect this line to be roughly halfway along this position. Obviously, if there's 48 minutes in a Stonehenge hour, there are 24 minutes in the half hour. So 22 minutes past, we'd expect it to be practically halfway along this line. It's exactly where we find it. This is the T4 line striking our first on the hour position. This is pillar 21, gone from 10 to 11, the 11th hour. This is happening when the sun's at 115 degrees azimuth. On May the 5th, this would be happening at 8:48 local mean time, 24-hour time, which is on to the 11th hour, Stonehenge time. So I just want to show you the watch in this clip. Sorry, it pans across a bit. We do get a clear shot of the watch. So this is 8:44 GMT. This is reading in BST. So it'll be 8:44 on August the 25th. Obviously, we're not on our calibration date. At this point, the monument's actually reading early by 4 minutes. In this next clip, the sun was partly obscured by cloud cover, and so the line is really quite faint. You can just make out the T4 line shining down here. This is pillar 21, and we can see it moving off the pillar onto this gap here. The sun is at 128 degrees azimuth at this point. On May 5th, this will be happening at 9:36 local mean time. In terms of 24-hour time, that's 9:36. 30-hour time, 9:36 equates to 12. This was position 11, so this is position 12. I'll just show you the watch. So we can see it's 9:35 GMT. So at this point, the monument's reading 1 minute early in terms of GMT. 6 minutes later, as we can see here. And the reason we're seeing this is because the sun had come out at this point. The T4 line can be seen a lot clearer. In 6 minutes, it's obviously moved a certain amount, but we can clearly see that it's on the 12th position here. The time here is 10:24 GMT. This footage was actually captured a few minutes early. The intended time really was 10:26 on August 25th. At this time, the sun was hitting 143 degrees azimuth, so that was really the intended time. We've got it here a few minutes early, meaning that the line is just under a degree short of its actual target. Nonetheless, you can see that it is moving on to 143 degrees azimuth, and it's moving on to the next hour target, pillar 22. On May the 5th, it would have been hitting 143 degrees azimuth at 10:24 local mean time, equating to 13 AM Stonehenge time. We can see the T4 line is now the rear, pointing directly at this pillar here, marking position 13 or the 13th hour. So we've gone from 10:30, 11, 12, 13. Halfway along this pillar, this line will get so thin that we'll just have a block of shadow here, and this line will no longer be there. An aspect that I haven't discussed so far, obviously the builders of Stonehenge would have had no concept of GMT, Greenwich Mean Time. The times you've been seeing on the watch were in British summertime. I've been converting them into Greenwich Mean Time. The Stonehenge architects would have worked in local mean time, and there's actually a 7-minute difference between Greenwich Mean Time and local mean time for the location of Stonehenge, because it's 1.8 degrees from Greenwich. That's a 7-minute difference. So this actually means that we should be deducting 7 minutes from all of our GMT times. You'll have noticed that the times relating to the hours earlier on were early by a couple of minutes in most cases. When by the time we got to this clip, the sun is hitting azimuth 143 degrees at 10:26 GMT, so it's actually now 2 minutes late. So obviously, taking into account the difference between Greenwich Mean Time and local mean time, it's still running 5 minutes early. Just the kind of illusion of it becoming late at this point in the morning is caused by the difference in local mean time and Greenwich Mean Time, that 7-minute difference. Of course, as it carried on towards midday, the true sun does actually catch up with mean time. For midday and solar noon only ever occur a maximum of 15 minutes apart. So basically the process flips, and for the afternoon, where for most of the morning the monument was reading early, for most of the afternoon on the August the 25th it will then read late. To really understand more about why this happens, to understand more about the monument, about its calibration, you need to go to cypherworks.wordpress.com. You can also feel free to send an email provided here, and please spread the word about this. This is a new theory. It does require a wider attention to it. So if you're interested in this, if you think you know anyone that would be interested in this, please share it, tell people about it, refer people to this video and to the WordPress blog site. There is a download on there to a paper that I have written exploring earth clock theory. The paper's called Stonehenge, a proto-sundial with bias towards summer.